In this video, we're going to talk about Big Idea 2, a review of the concepts, but part 2, focusing on bonding and phases. So we already talked about polarity and nonpolar versus polar and intermolecular forces. We're going to get into more specifics of representing those molecules three-dimensionally. So we first need to know about Lewis structures. So refresher, Lewis symbols, right? Sulfur would look like this. The 6 dots represent the 6 valence electrons in sulfur. And we know that these atoms are going to get together to satisfy the octet rule, to have a full valence shell, to form a compound. Lewis structures, we are not going to review how to draw them right now, but we need to know the 2 things to check for if you've drawn a Lewis structure correctly. Number 1, the most important thing, do you have the correct total number of valence electrons? So for example, if you have the compound CO2, your structure needs to have, well, carbon has 4 valence electrons because it's in row 4. Each oxygen has 6 because it's in group 6, but there's 2 atoms of it. So 12 plus 4, 16 electrons. So your final structure better have 16 valence electrons in it. The second thing that you need to check for is octet rule. Or another way of saying that is a full valence shell. Does each atom have a full valence shell? Okay. However, there are a few exceptions to this rule of the octet rule. So for example, elements, what you need to know, in row 3, meaning left to right, and below, can have more than 8 valence electrons. So common examples that you need to be watch out for: phosphorus, sulfur, chlorine, iodine, bromine. These are the most common examples that I see, that you will probably see, that could have more than 8 valence electrons. So for example, SF6 is composed of an atom of sulfur and 6 fluorine atoms bonded to it. And now you might think this structure and say, whoa, Shar, that can't exist, because you have 2, 4, 6, 8, 10, 12 electrons around that atom of sulfur. Well, in fact, SF6 is very stable. Sulfur is in row 3. It has enough space, because it's in row 3, of its electrons to form more than 4 bonds, to have more than 8 valence electrons. But most important thing, check these things when you're drawing Lewis structures. Some Lewis structures have things called resonance structures. Resonance structures are the same compound, Lewis structures of the same compound, with bonds in different places. Okay? So for example, these are all Lewis structures for the nitrate ion, NO3-, which we know the first thing to check, nitrogen has 5, each oxygen has 6, so it's 5 plus 18, but since there's this negative charge, that's 1 extra electron. So 1 plus 5 plus 18, I need to have 24 total electrons in this structure. Okay? Now, the dots aren't drawn here, but if the dots were drawn, then that would give us the 24 electrons needed for this to be stable. So this structure right here could form. We could have a double bond to the oxygen up top. But that double bond could also be on the oxygen on the right, over here. Or it could be on the bond on the left, over here. These are all the same molecules, same Lewis structure, but the bonds are in different places. So these are called resonance structures, resonance forms. What's important to know? Well, this single bond we know is the longest and weakest compared to this double bond. So you might think, oh, this bond is stronger than these 2. But in reality, if you have a room full of nitrates, all of these molecules, thousands of them, what this is saying is that a third of them will look like this, a third will look like this, and a third will look like this. We can prove that they're all equally energetic by calculating something called the formal charge. So formal charge is the number of valence electrons the atom should have minus number of electrons and bonds around it. So for example, we calculate the formal charge on atoms. So this atom here, okay, if we drew all the dots in, just because they should be there, Why does it have a little negative sign? Well, that little negative represents the formal charge on that atom. Well, if we calculate the formal charge of this, it would be equal to the number of valence electrons, so oxygen should have 6 from the periodic table, minus the number of electrons plus bonds it has. So it has 1, 2, 3, 4, 5, 6 electrons and 1 bond. 6 minus 7 equals negative 1. That's where this negative comes from. This nitrogen, on the other hand, has a positive 1. Well, let's calculate the formal charge on it. Formal charge equals the number of electrons nitrogen should have on the periodic table, 5. Now let's count how many bonds and electrons. Well, there's no electrons around it, but there's 1, 2, 3, 4 bonds. Plus 1. So that's where the positive comes from. If you add up all the formal charge, it better equal the overall charge on the compound. So nitrate has an overall charge of negative 1. So all the formal charges together better equal negative 1. So negative 1, negative 2, 0, so we're still at negative 2. Positive 1 gives us the negative 1 overall. So that's how we can check if our structures are drawn correctly. Back to the bond thing here. Since these are all equally energetic, in reality we don't have a double bond here, or a single bond here, or a single bond here. We actually kind of have all of these structures existing at once. So essentially each one of these is kind of like an in-between 1 and 2 bond, like a 1.5 bond or something. So they'd all have the same length, and they'd all require the same amount of energy to break. This gives way to something called valence shell electron pair repulsion theory, VSEPR. This is basically our molecular geometry. So your molecular geometry, you just need to have those structures memorized. So what do you need to know? For example, if you have, one electron group, let's do 2 electron groups and 0 lone pairs, you need to know a few things about that. Number 1, you need to know the name of the shape, linear. You need to know the bond angle. Number 2, which would be 180 degrees for this molecule. And number 3, you need to know the hybridization, which is sp3. These all just come from your molecular geometry sheet. I'm not going to go over them all right now, but I'll draw an example molecule of this. If it has 2 electron groups, something that's just like, CH, like this. This doesn't exist, but this would be 2 electron groups, no lone pairs, 180 degree bond angle here, and sp3 hybridization. sp hybridization, which means it's formed from one s orbital and another 1p orbital come together to make the sp orbital. Remember, the exponents here kind of represent how many orbitals were used to make that hybrid orbital. So valence shell electron pair repulsion, you need to know your molecular geometry. Common mistakes to watch out for with molecular geometry, let's say you have CH4. The Lewis structure for CH4 methane looks like this. And your natural inclination would be to say, oh, here's a bond angle of 90 degrees. But that is wrong. Remember, this is 3-dimensional. So these hydrogens want to get as far away from each other as possible because these electrons are repelling. So this actually is a tetrahedral shape with a 109.5 degree bond angle. Again, you need your molecular geometry sheet to review those, but you need to know these 3 things about any compound. Compounds, specifically in Big Idea 2, we talk about gases a lot. The ideal gas law, PV equals nRT. What do you need to know about this? The gas constant R, 0.08201, which is liter atmospheres over mole Kelvin. You need to know this constant. It's on your equation sheet, but you need to know the units for it more importantly. Because if you're using the ideal gas law, temperature needs to be in Kelvin, volume needs to be in liters, and pressure needs to be in ATM in order to use that number. What does the word ideal mean? An ideal gas is a gas that behaves ideally. So what does that mean? The molecules, the gas molecules themselves, have no volume. So for example, if you have a balloon, there are molecules floating around. We can measure the volume of the whole balloon, but we're saying that these individual molecules have no volume, or it's so small and insignificant it doesn't affect the volume of the whole balloon. When do gases behave ideally? Ideal conditions are when you have few/no interactions. If molecules are interacting with each other, they are not behaving ideally. So how can we minimize the number of interactions? We can increase the temperature. So we want high temperatures for gases to be ideal, because that means the molecules are moving around so fast that they don't have time to interact with each other. And we also want very low pressures. Low pressures means we're not forcing molecules to interact. They can be very spread apart. They're not confined to a small space. So under these conditions is when a gas behaves most ideally. When is it the least ideal? It'd be the opposite. At a low temperature and a very, very high pressure. So we can collect data on this. This is shown in the graph here. This dotted line represents an ideal gas. The closer you are to that line, the more ideal you are. So first you can see, at a pressure of 600 atm, 1000 Kelvin versus 600 versus 200. At 1000 Kelvin, we're closest. So this shows our high temperature means a gas behaves more ideally. If we look back at, as we go this direction, just follow one of the lines. We can see as we go back to the left, the line gets closer to ideal behavior. And as we go to the left, we have low pressure. So again, low pressure, high temperature means a gas behaves ideally. The last thing we need to talk about with gases is Dalton's law of partial pressures. So this applies to mixtures of gases. Okay? So for example here, if you took gas A, B, and C separate and combined them together, the total pressure of that gas is equal to the partial pressure of A plus the partial pressure of B plus the partial pressure of C. So if this is 5, these could be 2, 1, and 1. Well, now how do we figure out the partial pressures? Well, they depend on how many moles you have. The more moles, meaning the more molecules you have, the higher the pressure of the gas will be. So that's another way that we can represent Dalton's law of partial pressure. So for example, let's say we wanted to know the partial pressure of gas A, these blue dots here. The partial pressure of gas A would be equal to the total pressure times what's called the mole ratio, which we label with an X, which is the same thing as the total pressure times the moles of A over the total moles. So remember, just think of this as a fraction. The idea is if you have more moles of A, out of the total moles, like if you have 5 moles of A out of 15, that means a third, 5 over 15, of the total pressure depends on gas A. On the other hand, if you had, gas B, and let's say gas B was composed of 1 mole of B out of the 15 moles, okay? Then you know that 1/15 of the total pressure is because of B. So the partial pressure of A would be greater than the partial pressure of B because there are more moles of that gas present. So we need to know how to do those manipulations. You could weave in stoichiometry here. I could give you grams and you would have to convert to moles. You could have an equation, A going to B plus C, where the mole ratios here, 1, 1, tells you how many moles of gas are being formed. There's a lot of ways that can be woven in, but you need to know basically this representation, which is on your equation sheet, and that it means this, ideal gas law and behavior, as well as our understanding of molecular geometry, resonance structures, calculating formal charge, as well as how to draw Lewis structures and check if they're drawn correctly.